So we've talked about oscillations. Oscillations are things that, like a weight on a spring or something like that. Here's a spring with an oscillation. If the oscillation just goes back and forth like this, right? That's an oscillation. But a wave is a repeating traveling disturbance. And so that means it's traveling through space. In addition to oscillating, it's also moving. And that's different than just an oscillator, which just stays in one place and oscillates like a pendulum or a weight on a spring. There are broad categories of waves. You can see the definition is kind of vague, a repeating traveling disturbance. It doesn't have to have any particular shape or any kind of way of oscillation. It's just repeating as it's moving. And examples like ocean waves, we don't really see the wave in sound waves or light waves, but we can certainly see the patterns they give. And so there are two basic types of waves. There are lots of types, but two basic ones. The first one is transverse waves. Transverse waves oscillate perpendicular to their direction of motion. So if they're moving this way, they're oscillating this way. It's easy to draw a transverse wave, and mathematically we can address everything. We can treat everything as kind of like a transverse wave because the math will look the same. But the way you can draw a transverse wave is just take your arm and cause it to oscillate up and down like this, and then just drag it. Oops, I bumped something. And then just drag it forward while you're doing that. So let me try that one more time. I can just go like this, and then if I just pull it, I get a wave out of that. And so an example of this is light waves, waves on a rope. You can kind of see it. I can take this slinky and kind of make a transverse wave on a slinky. If I go like that, I would have to keep doing it to make it repeating, but you get the idea. Right? And so that's a transverse wave. I kind of messed up my writing there, but that's okay. Type 2 is longitudinal waves. Longitudinal waves oscillate along their direction of motion. And that may seem a little weird, but an example of this is like sound waves. And there are others. And I can do a longitudinal wave on a slinky as well. A longitudinal wave looks like that. You see those waves traveling down? Those are longitudinal waves. The oscillation, whereas for a transverse wave, the oscillation is up and down while the wave is traveling that way. When a longitudinal wave, the oscillation is this way while I'm traveling that way. And so those are different from that standpoint. And it turns out sound waves are longitudinal and light waves are transverse. We'll see that they're actually represented mathematically exactly the same way. So let me talk about a few properties of waves. So for the sake of this discussion, I'm going to just draw some waves. It's easier to do it on a blackboard than on a large board than on a small board. Imagine this was a reasonably well drawn wave. So basic properties of waves. So one is wavelength. That's the distance between any two like points on the wave. And maybe I should say maybe here I should say successive. So the wavelength is the distance between two peaks, or I could say this is also a wavelength, the distance between two troughs, that's also the same distance. Or I could pick, halfway down the slide to halfway down the slide, this is also a wavelength. So I could pick any two like points, successive like points on the wave, and the distance between them is the wavelength, right? 2 is the amplitude. The amplitude is just the maximum displacement from equilibrium. And so, if this is, say, a water wave that's traveling along the water, or maybe this is a wave on a rope, right? This would be the amplitude, right? It's the maximum displacement. The equilibrium position is halfway down the middle, right? And the maximum distance from equilibrium is called the amplitude. By the way, the amplitude doesn't have to be a distance. For a pressure wave, like a sound wave is kind of like a pressure wave, the maximum pressure would be the amplitude. And so just depending on what it is that's oscillating. In light waves, the thing that oscillates is the electric and magnetic fields. And so the amplitude in a light wave is the electric field. But often it's distance. 3 is frequency. So the frequency is the number of waves passing a given point in a given time period. And so if you can imagine this is a water wave, right? And I'm standing here, happy to be in the ocean, right? If 2 waves go by me per second, then the frequency is 2 per second, or 2 hertz, right? And so that's wavelength, amplitude, and frequency. All of those matter. I'm going to talk a little bit more about those here in a second. And so my argument, k times x, must have gone up by 3 times 2 pi. And so this means k must be equal to 2 pi over the wavelength. So that anytime x increases by lambda, the whole solution increases by, the whole argument to the cosine increases by 2 pi, and I get the repetition. And so k is equal to 2 pi over lambda. It's often called the wave number. Just like the omega we used for oscillations was 2 pi over the period, k is 2 pi over the wavelength. An interesting thing to note about this is that this wave is not traveling. That is to say, there's no time dependence in this picture. And so we've still got to figure out how to incorporate time into this so that my wave can move. I haven't done that yet, but at least as far as the spatial extent of my wave traveling along my rope, this represents it. So I just want to talk for a minute about the speed of a wave. So if I have a wave that's going this way at velocity v, and I want to know what its speed is, well, this is its wavelength, right? So if I'm standing here, then, so let's say I'm just an observer here, right? The speed is just distance over time, but that's equal to just the wavelength over the period, right? The period is the time it takes to go from one point to the next, and so to go through one complete wave, and the distance for it to travel that far is the wavelength, and so the speed of a wave is the wavelength divided by the period, or the wavelength times the frequency. We already said the frequency is 1 over the period, and so this is a standard relationship for all waves, that the speed of the wave is equal to the frequency times the wavelength. Or you could write it as the wavelength over the period. Normally when you're talking about waves, you talk about the frequency and not the period. So like for radio stations, the Coyote here is 95.5 megahertz on FM. And so usually you're talking about the frequency. So now we have a wave that's traveling this way, say, and what we said was if it's just a stationary wave, I can just represent it this way. I can say y is equal to a times sine of kx plus some phase, and if this is my if this is my coordinate system, there's y in my x direction, right? In this case, I have a cosine, so that would be a pi over 2, and k is equal to 2 pi over lambda. Right, that's what we said. K has to be so that the wave cycles every time x increases by a wavelength, the argument to the sine function increases by 2 pi. And so that's how that works. But now we have to incorporate time here. This wave has no time dependence. I want my wave to travel, say, at some speed v. To the right, the wave you see there, that function y equals a sine of kx plus phi naught, is a stationary wave. It's just standing there, and so the way you make it move is you say y is equal to a sine of kx, and you can either have plus or minus omega times time plus this phase. And again, so this starts to look a little complicated, but remember, this part was just an oscillator that oscillates up and down, and this part indicates the position. And so if you look at this a little bit, you can say, well, suppose you fix the position, let x equal 0, and we want to watch what happens at the origin, right? Well, y will oscillate up and down just like an oscillator at a given x position. So if I fix x equals 0, then I have a sine of omega t plus phi. That's just an oscillator, right? And that's what would happen if you were just looking at the origin as this wave was going by. First it would go down and then up, right? You're standing at the origin and this wave is going past you. First it goes down till it gets to this point is here, and then it goes back up and down and up. And so every point at every fixed x has it's like it has an oscillator at that point. And so it turns out that if a sine of kx plus omega t plus phi naught is a wave moving to the left, it's a wave going to the right. Notice that this is the same k where k is equal to 2 pi over lambda and omega is equal to 2 pi over the period. And so the velocity, which is equal to the wavelength divided by the period, the velocity of this wave is equal to omega divided by k. And so if you give me this wave, its amplitude is a, its wavelength is can be determined from k, it's 2 pi over k, its period is 2 pi over omega, and its velocity is omega over k. And so you get that all out of the wave, all out of the function of the wave. So I can kind of explain to you why, I'm going to show you in another video, but I can kind of explain to you why this one is a wave moving to the right, right? So if you, again, pick x equals 0, so we're just looking at this spot, right? Then if I have a minus sign here, the next thing that's going to be at the origin is going to be at minus omega times some time interval. And so when I put a minus sign in here, these guys are going to be moving towards the origin this way, and so my wave's moving to the right. In the same way that if I have a plus omega t, as time increases, the things that are going to be at x equals 0 are going to be to the right. And so this will be a wave moving to the left, and this guy will be a wave moving to the right. So this is our this is a standard wave. This is the formula we gave for it: the amplitude times sine of kx minus omega t plus phi. I put a 1 subscript on all of this, just in case we want to put a second one in here. K is again the wave number, omega is the angular frequency. Because I have a minus sign here, then as t increases, the wave will move to the right. And you can see that here's my time bar, and watch me just slide it to the right, and you'll see the wave take off to the right. Right? I'll put time back to 0 there. Notice that my phase here is 0, and so I have a sine wave. You can see it where it crosses the y-axis is at 0, increasing to 1. If I wanted to, I could change my phi to my phase to pi over 2, which is about 1.57, somewhere in there, and I have a cosine wave, right? So let's go back and put it at 0 for now, right? We can mess with a few. We can mess with a few of these other. Yeah, my phase is 0 again. So we can mess it with a few of these other coefficients. Here's the amplitude. It's set at 1.6, which is kind of arbitrary. I can kick it up to 2, and you can see that just increases the amplitude, right? Notice we said the wave number was 2 pi over the wavelength. And so in order for k to get bigger, the wavelength has to get smaller. And so if I drag the k slider to the right, you'll see the wavelength get more compact, right? As I move it to the left, it gets bigger and bigger until it gets ridiculously straight at k equals 0, because that means the wavelength is infinitely long. And so I can put it in here somewhere where it's a reasonable number for us. And so the frequency is really how fast the wave is moving. So if I'm standing at one spot here, like if I'm standing at x equals 2 over here, the frequency that I see is determined by how fast the wave moves to the right. And so I'm going to set a really low frequency here. Let's set the angular frequency like 0.1 or something. 0.1. And as time goes by, you'll see, as time goes from 0 to 10 seconds, the wave is barely moving. It's got a very slow angular frequency. I'm going to go back to 0 a couple of times, and it's just barely moving to the right, right? But I can give it a larger angular frequency. Remember, angular frequency is 2 pi over the period, right? And so if I have a high angular frequency, I have a short period. Let's get a number out here. And now you'll see as the time increases, it's moving fairly quickly to the right, right? Again, the velocity is the wavelength over the period, and so that's omega over k is the velocity. I think that covers it. So now I've inserted a second wave. It's all in blue, and I can again adjust the amplitude to anything I want. I can adjust the wave number to anything I want. Maybe we'll leave this one a little bit bigger. I can adjust the phase. Maybe this one will be set t equals 0 here. If t equals 0, these are both sine waves, right? Let me pull this out so we can see it a little better. I'm going to put it in between them, maybe something like that, right? And so this has all 2's. Oh, this should have a, let me just pull that up here in a second and put a 2 there. Underscore 2. So that I have a 2 subscript on there. Right down here is where I want that. And then I can move the, I can move the, notice this one, the blue wave has a plus omega t, and the red wave has a minus omega t. And so as time increases, the red one is going to move to the right, and the blue one is going to move to the left, right? And so let me get my time back to 0. I can have a really slow velocity, angular frequency on the left for the blue one, and a high one for the right. And so you'll see as time goes, the top one will move fast to the right, and the bottom one will move slow to the left. And so these are how we control the wave with these different parameters. Whoops, I kind of goofed that, didn't I? Let me just put that parenthesis back in there. There we go. All right, it doesn't matter. So that's a little bit of a look at the wave numbers and the angular velocity for a wave traveling to the right and to the left. By the way, I just shifted this one, the blue one, downward by adding -3 to it, but it could just as easily be running through the y-axis, through the x-axis as the red one is. It just gives you a little better look at them. At some point we'll do interference, and we can add these things as they're going past each other.